Volcanoes weakened the dinosaurs while asteroid dealt the knockout blow. Mass extinction recovery governed by morphospace. Slow return to diversity is due tensions between ecology and possibility. Stephen Fleshfresser reports on Cosmo magazine. The reestablishment of species diversity following an extinction event is consistently slower than evolutionary theory predicts. Theory tells us that after a mass extinction, an event where the diversity of species is drastically reduced, nature should rebound with a flurry of creativity. Species should quickly proliferate to refill desolate ecosystems, something called adaptive radiation. Yet, the paleological record suggests that this does not happen at anywhere near the expected pace. Now, research published in the new journal Nature, Ecology and Evolution argues that understanding something called morphospace might help us find the cause. Extinction events happen with alarming regularity. There is the Big Five, but a host of slightly smaller yet still devastating extinctions have peppered the planet's history. Scientists now worry that we might be in the middle of one of our own making, so this makes it all the more important to understand how the natural world bounces back from such catastrophes. Perhaps the most well-known of the Earth's mass extinctions is the Cretaceous Paleogene, the KPG extinction event. This took place about 66 million years ago when an asteroid smacked into the Earth next to what is now the Yucatan Peninsula, creating the nearly 200-kilometer wide depression known as the Chicxulub crater. This impact drove the extinction of all the non-avian dinosaurs and much else besides. In a new research, Christopher Lowry of the University of Texas Institute of Geophysics and Andrew Frass from the Sam Houston State University, also in Texas, argue that the recovery of various forms of plankton, or more formally planktic foraminifera, was usually slow. What should have been a classic example of explosive adaptive radiation happened in waves over time, the latter of which were delayed for millions of years, they write. The diversity of species did not return to mid-Cretaceous levels for 10 million years, and only reached late Cretaceous levels after 20 million years. The hypothesis put forward to explain the slow recovery marine plankton have mainly centered on the environment, such as toxic metal left by the asteroid or the impact-linked volcanism. Lowry and Frass note, however, that evidence is sparse for these explanations. Instead, they argue, quote, that ecology rather than environment controls diversification after mass extinction, unquote. And an important component of this is the time needed to reconstruct morphospace within ecosystems. This they call the morphospace reconstruction hypothesis. Morphospace, short for morphological space, is a way for scientists to visualize the possible shape and structure of organisms, the physical phenotype. The morphospace can show all possible forms and how many of those have been taken on by organisms in the real world. Ecological niches are formed by the pairing scientific and environmental conditions with the phenotype of species, and this can be more properly conceived of as morphospace, that is, the range of morphologies occupied by clade. The authors write, this represents a range of successful strategies that a clade has evolved to adapt to its environment and pressure from other organisms. As organisms undergo adaptive radiation after an extinction, they begin to colonize different parts of the morphospace. These new morphologies or phenotypes, quote, can serve as a jumping-off point for further evolutionary innovation, unquote. This in turn provides a new point of evolutionary departure and further opportunity for morphological innovation and complexity. What Lowry and Frass discovered is that the fossil record for marine plankton shows that increasingly complex morphologies are linked to episodes of taxonomic diversification, with the latter being dependent on the former. Newly occupied morphospaces open up room for increasing radiation, just as morphospace reconstruction hypothesis predicted. Importantly, their work indicates that the constraints of morphospace colonization might impose a speed limit on post-extinction taxonomic diversification. This is a sobering reminder that if we are in the midst of an anthropogenic extinction event, the biosphere will take millions of years to get over it. And even when it does, it will be a very different world from the one we're inhabiting now. This by Stephen Fleischer, lecturer at the University of Melbourne's Trinity College. He holds a PhD in the history and philosophy of science and is on Cosmo magazine. Volcanoes weakened dinosaurs while asteroid dealt the knockout blow. Gases spewing from inside Earth triggered a mass extinction 66 million years ago. Not the meteorite, new work suggests, but teasing apart the two events is easier said than done. This is reported by Belinda Smith on Cosmos magazine. Long sustained outpourings of lava and gases from what is now India put ecosystems under stress before the asteroid hit 66 million years ago on Earth, new research suggests. What finished off the non-avian dinosaurs, along with 3/4 of the planet's species, 66 million years ago. A trio of geochemists in the U.S. claimed the famous meteorite impact usually attributed to their extinction was preceded by a massive bout of volcanism a few 100,000 years earlier. This weakened ecosystem the systems around the world and set up species for the asteroid to deal the knockout blow. Their work was published in Nature Communications. The cause of the mass extinction at the boundary of the Cretaceous and Paleogene periods is still intensely debated, while the meteorite that struck what is now Mexico has traditionally been the forerunner megavolcanism in India, which spewed monstrous floods of lava and gases for tens of thousands of years to form the Deccan traps, has gained traction. Most scientists think a combination of the two dealt a 1-2 punch, but some say the impact shook up the Earth to trigger the eruptions, while others said the volcanoes were already in full flow when the asteroid hit. The problem is untangling the timing between the two. Which came first, the blast from outer space or rumblings deep beneath the Earth? Dating these events millions of years old is tricky. The most reliable dating method have error margins of a few 100,000 years, and an incomplete fossil record does not help either. So Sierra Peterson and Kiger Lohman of the University of Michigan and Andrea Dutton of the University of Florida turned to mollusk shell fossils from Seymour Island in Antarctica, which grew during the last few million years of the Cretaceous and across the extinction boundary, around 69 to 65.5 million years ago. They used a new geochemical technique called carbonate clumping isotope paleothermometry to ascertain sea temperature changes during the period. The temperature of the ocean's surface dictated what isotopes of elements, atoms with different numbers of neutrons in their nucleus, are present. Warm water, for instance, tends to see more of the lighter oxygen isotope O16 evaporate, leaving a higher ratio of O18 in the ocean. And mollusks keep a record of this O18-O16 ratio and other isotopic ratios in their calcium carbonate shells. Over time, the mollusks died and were buried in layers, and their shells dug up and analyzed. Peterson, Dutton, and Lohman, analyzing many different isotope ratios in 29 fossil shells, found a temperature spike that coincided with the onset of Deccan Tramp's volcanism and another smaller peak around the time of the asteroid impact. Before either of the pulses, though, was a period of sustained warmth. Around 68.7 to 67.8 million years ago, temperatures rose from 5 degrees Celsius to 14 degrees Celsius. The water stayed warm around 9 to 12 degrees Celsius for a million years or so, and then gradually cooled to 4 degrees Celsius by 66.25 million years ago. Then only around 150,000 years before the meteorite impact and around the time the Deccan traps started to stir, spewing greenhouse gases into the atmosphere, came the first temperature spike around 7.8 degrees Celsius plus or minus 3.3 degrees Celsius. This was followed by cooling and a second smaller peak of 1.1 degrees centigrade plus or minus 2.7 degrees centigrade at the time of the impact. And over the next 200,000 to 400,000 years, the temperature dropped to pre-impact levels. The mollusk measured spikes in temperature also coincided with marine species extinctions. The first pulse, dated 66.23 million years ago, saw 10 species disappear from that layer. 9 were benthic, or bottom-dwelling. The second pulse was 14 species wiped out, but only 6 were benthic. This, the researchers write, suggests different kill mechanisms for each, such as volcanism versus impact. The reason those species did not die in the initial period of sustained warmth is they had because the temperature rose gradually, and when faced with sudden volcanism and impact heat spikes, though, they were unable to adapt in time. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.